Hello and welcome to a Fuels Friday video about fuel weight and bulk density. My name is Dave Schroeder and my colleague Steve Vienegard and I will be your narrators. This video is organized into three sections. We will start by covering some definitions and then go into a bit of depth with a case study. The case study will demonstrate why fuel weight and bulk density are both important for fire behavior understanding and forecasting. We'll wrap up with some general considerations for planning data collection to obtain these parameters. You will also see fuel weight and bulk density covered in other Fuel Friday presentations and videos, an indicator that these are important parameters. Bulk density and fuel weight are common parameters used to describe fuel structure and are used in fire growth prediction models either directly or indirectly. For example, the Rothermel surface fire model includes a bulk density parameter, whereas the present version of the CFF-DRS fire behavior prediction system uses fixed fuel weights and bulk density associated with specific forest fuel types. Other models, such as CAN-FIRE and CFIS model, which we'll use in our presentation demos, allows users to input fuel weight or bulk density values. Fuel for this presentation refers to organic material, living or dead, that can ignite and burn. Fuel load is often used interchangeably with fuel weight. Bulk density refers to the weight of the fuel per unit volume. This simplified demonstration shows how flammable material with the same weight will burn differently when bulk density is changed. On the left, the 8x10 sheet of paper has been tightly folded and the bulk density is highest relative to the other pieces of paper. The piece in the center has been tightly crumpled and the right piece has been lightly crumpled. You can see the variation in fire behavior, and the folded piece will not even sustain an open flame. The video demonstrates two important fuel parameter considerations for fire behavior. First, bulk density can affect the rate at which fuel is consumed, and second, bulk density will affect the proportion of total fuel weight that is burned, and as such influence the amount of available fuel for combustion. As the video demonstrated, fuel with the same weight but different bulk density values will burn differently. The question then is, why bother with fuel weight? First, fuel consumption by weight is the basis for Byram's fire line intensity calculation, so we need the weight of fuel being consumed. Another reason is that collecting fuel weight is much more straightforward than bulk density. For example, reliable and efficient methods have been developed to sample dead and down woody fuel weight. Similarly, tree biomass weights can be calculated using one easy-to-collect measurement, diameter at breast height. Adding fuel depth in order to get bulk density is straightforward for some fuels, but can also add complexity and effort to collect the data, as we will demonstrate. As well, an accompanying video focuses on challenges specifically associated with measuring one important parameter used to obtain fuel depth, canopy base height. The values at the bottom of the slide show canopy fuel load and bulk density for two adjacent sample plots from the same stand of black spruce trees. You can see that both these stands have very similar canopy fuel loads, or CFL, but quite different canopy bulk densities due to differences in tree height. Wildfire management is increasingly focused on mitigating risk around communities, infrastructure, and other values. One way that agencies address this challenge is to use a variety of vegetation management techniques intended to reduce wildfire hazard. The importance of vegetation management around the wildland-urban interface is a driver for much of the current fuel structure research. As you can see in the list on the slide, changing fuel structure can be an important strategy within the overall goals of a wildfire mitigation plan. Vegetation management plans can benefit from having targetable measures, such as reducing fuel weight or bulk density to quantifiable values. We'll now move on to part 2 of this video. In some jurisdictions, the tactic of masticating or mulching vegetation has been used to displace fuels from the canopy to the surface. Mulching is not as effective as fuel removal to mitigate fuel hazard, but is more cost-effective to implement. Test burns in mulched black spruce stands indicate that fires in mulched fuels are less intense and slower moving relative to natural stands, and as such are more likely to be suppressed. In part 2, Steve will demonstrate how fuel weight and bulk density affect fire behavior in mulched fuels, and will present some of the challenges to collecting this data.
In the introduction, 4 vegetation management principles were presented. Generally, in mulch fuel treatments, displacement is the primary principle applied by converting canopy fuels and surface fuels to a more compacted layer of woody debris. Several different techniques are used with various machine types to create unique fuel beds, each having different characteristics such as fuel particle shape and size and fuel bed depth. The fuel bed in this right-of-way is unique in the uniformity of debris size and distribution. However, this homogeneous fuel bed may be more of an exception, as most masticated fuel beds include other fuels such as grasses and shrubs. Every fuel bed has different characteristics that influence fire behavior. In mulch fuel beds, compaction of chip debris and other fuel particles influences airflow through the fuel bed and the rate that fuels dry. Compaction can also impact fire spread and fire intensity. Can bulk density be used as a measure of compaction and used to calculate potential fire behavior in a mulch fuel bed? Destructive sampling is often conducted to determine the fuel load and bulk density of mulch fuel beds. This process and calculation of values is very straightforward in a uniform fuel bed such as this one. In a study of potential fire behavior in debris fields in hydro rights-of-way, we evaluated the debris using destructive sampling to determine bulk density and then determine the volume of fuel assumed to be available for combustion. Bulk density was determined through destructive sampling in several mulch pits. From previous experimental fires and moisture sampling, we observed that fuels deeper than 5 centimeters were too moist for consumption. Using this as an assumption, it follows that available fuel equals 6.3 kilograms per meter squared. But this seems like a large loading of fine fuel available for consumption. What kind of fire could be expected in this fuel bed? Most fire behavior prediction tools don't model these fuel beds well, but attempts at modeling fire behavior have been made using Behave Plus. This projection in Behave Plus, using 90th percentile conditions, indicates fire behavior with low intensity and low rate of spread. Experimental fires in mulched fuel beds have given us good insights into potential fire behavior in these fuel environments. Unit 2 at the Pelican Mountain Fire Smart Research Area was designed to study fire behavior in mulched fuel beds that have been treated using varying treatment intensities. 3 different mulch treatment prescriptions with varied intensity were applied in the 3 subunits. This resulted in 3 distinct mulch fuel beds with different fuel characteristics. Coarse mulch was produced using a low-intensity mulch treatment with 1 pass to knock over stems and remove branches. Key characteristics of this fuel bed include a greater volume of roundwood debris, a lesser amount of mulch debris, and a relatively undisturbed surface fuel layer. A normal mulch intensity is the standard typically applied in industrial operations such as clearing for industrial sites or right-of-way maintenance. The regular mulch fuel layer has most aerial and surface fuels processed into chip debris. Some disturbance of the duff layer occurs but is generally not prescribed in mulching operations. A high-intensity mulch treatment thoroughly mulched all vegetation and mixed this with the duff layer. This resulted in a fine mulch fuel layer with a higher percentage of smaller debris and a greater extent of mixing with duff and some mineral soil. In characterizing these fuel beds, bulk density was considered as a metric to compare compaction of the fuel beds. We applied the data collection methods described earlier to determine fuel load and fuel bed depth. and these measurements resulted in some confounding results in that bulk density of all these fuel beds was similar at 150 kilograms per cubic meter. This didn't seem like an intuitive result since we expected that there would be a greater difference in bulk density to reflect the apparent differences in compaction. A possible explanation for this was that with only 5 depth measurements per quadrat, this did not accurately capture the scattered coarse mulch or roundwood. Therefore, alternative sampling methods need to be considered. Moving past the characterization of these unique fuels, our next objective was to observe and compare fire behavior in these distinct fuel beds. In these simultaneous burn trials, in the 3 fuel beds, there were some notable differences in fire behavior. Flame length, rate of spread, and depth of burn were measured and analyzed. We observed the most vigorous fire behavior in the coarse mulch fuels. We attribute the greater fire intensity and more rapid rate of spread to an undisturbed surface layer with greater continuity, which promoted more efficient fire spread. In contrast, fire behavior in the fine mulch fuel bed was relatively subdued with low flame height and slow rate of spread. The compacted mulch fuel bed with lack of vertical continuity inhibited fire growth and generation of fire intensity. Fire behavior in the regular mulch fuel bed was close to that of the fine mulch fuel bed. The intact moss layer and other undisturbed surface fuels contributed to slightly greater rate of spread and fire intensity. These observations of fire behavior in these burn trials in the different mulch fuel beds provides decision support for practitioners applying mulch treatments in boreal forest stands where high-intensity mulching is an option. The results calculated for bulk density prompted some pause for thought in how we measure fuel bed depth in these variable fuel loads.
As Steve indicated, our initial mulch sample data did not reflect the observed differences in bulk density. We concluded that the initial sampling technique that only captured the average bulk density was too coarse. Because of time constraints, we could only do some informal remeasurements where we collected samples in 10 centimeter vertical increments. This process resulted in a lot more time needed to collect the samples, but results suggested we could now differentiate between the treatments based on bulk density. Here's another example using grass fuel types. The Alberta Wildland Fuel Inventory Program has conducted some exploratory data collection for grass fuels in Alberta. The intent was to better understand differences between matted and standing fuel types and how to determine the degree of curing. In the FBP system, degree of curing is an input for the grass fuel models, and assessing that value is largely a subjective call at present. The matted grass in the photo on the right was sampled in the early spring prior to green-up. That matted grass is still there in the summer, along with new growth, as shown in the photo on the left. From a fire behavior perspective, the grass in the left photo is likely to be classified as greened up, and will in reality support little, if any, fire. Strictly by weight, however, the total sample would indicate a high degree of curing because the dead matted grass has much greater weight in proportion to the new green grass. Stratifying the samples vertically helped to differentiate cured and green grass, but added a lot of effort to collect the data. To wrap up, we will show some examples of challenges around using new data in an existing fire growth model, and will present some considerations of scale when collecting data or applying models. The final slides are about change. Good fuels data, including weight and bulk density, are relatively scarce. In order to improve that, new methods of collecting data are needed, along with potentially new or modified fire behavior models. Practitioners are challenged with using models or data that are not sufficient for their needs, whether that is for fire operations support or planning a mitigation project. On the other hand, researchers are interested in working on solutions for practitioners that may require adapting to new processes. In reality, introducing change to well-established models like the FBP system is not straightforward, nor is the implementation or uptake of new models. Here are two examples where applying fuel weight or bulk density to models needs to be done with careful consideration. The Crown Fire Initiation and Spread, or CFIS, suite of models was built on a wide range of wildfire data sets and allow users to input their own fuel structure data. The models did not include wildfires with mulch fuels explicitly, so use of mulch fuel weight as an input could result in misinterpretation of potential fire behavior. In the second example, again using the CFIS suite of models, we show a graph where a detailed vertical profile of the canopy bulk density for a stand does exist, but the model only accepts one input. In the case of CFIS, there is quite a bit of documentation supporting the model development, inputs used, and sensitivity to input parameters, so users can make an informed decision from the literature. We will conclude the video with a brief discussion about scale. Going back to this diagram shown at the beginning of the video, a few things come to mind. First, the images represent a small forest stand at a spatial scale that resonates with human observers. One can easily see the variability within the stand both horizontally and vertically. And it is straightforward to imagine that through time some of the overstory trees will die and fall over, and many of the understory trees will become dominant, resulting in changes to fuel weight, bulk density, and other fuel structure parameters. Fuel weight and bulk density quantities change through time, and that occurs for many reasons. Accounting for sampling timelines is an important consideration when applying fuel structure data to a model or other analysis. For example, forest inventory data sets may be used by agencies, where available, to categorize forest canopy data into FBP fuel types. Forest inventory data, however, is collected at variable time intervals, and at a provincial scale, when it's aggregated, will feature data representing variable snapshots and times, sometimes spanning 20 years. Moving to spatial scale considerations, at a plot level, the photos in this slide show a black spruce stand sampled by the Alberta Wildland Fuel Inventory Program. The plot radius is 11 meters, and you can see that there are some openings and dense canopy within the plot. Normally, plot level fuel weight and bulk density calculations will be aggregated to a larger stand, but will the aggregated data be representative of that stand? The reality is that natural forest structure is highly variable, as the photos show. A companion video demonstrating the use of LiDAR data to map fuel structure shows that this variability can be captured at a very high resolution. Zooming out, this photo shows an aggregation of fuel type patches, and the fire seems to be burning more intensely in the dark green patches. The light green patches are likely fens, and the dark green patches will be black spruce stands. From the previous slide, we saw that black spruce stands can be quite heterogeneous in terms of fuel weight and bulk density. Is that variability influencing the fire behavior at this scale, or is coarser data more appropriate? Zooming out even further, this hazy scene contains a larger mosaic of upland deciduous forests, black spruce stands, and fens in the mosaic, and a fire in the background. How are fuel weight and bulk density important at this scale? Or do other fuel structure parameters have more importance? Fuel weight and bulk density data are important information for fire behavior research and operational forecasting. The data are expensive to collect, and as such, we don't have enough relative to our needs. As accompanying workshop videos will show, new technology has much promise to meet this need, but also the potential to be misapplied. Thank you for watching this video, and we hope you enjoy the rest of the Fuels Friday workshop.